Okay, so Happy New Year, everybody. Welcome to 2025 season of the IAMP seminar on mathematical physics. And we are happy to have today Wendelin Werner from the University of Cambridge, who will talk about percolation of loops and the Gaussian free field. Please go ahead.
Okay, thank you very much. I hope there will be no technical mishaps and that everybody can hear me well. Thank you very much for the opportunity to speak to this nice community worldwide. So when preparing my lecture, I realized that probably the best option was to spend first half at least of the lecture to some general framework and historical perspective on things rather than jumping into trying to announce the very recent stuff. Probably I'll touch a little bit about that at the end, but that's sort of not my main goal here. It's sort of more to give you an idea of what we are trying to do on this these days on these questions. Maybe the one good point to start with is that for somebody like me who was sort of brought up on the probabilistic community and sort of entered then after studying Brownian motion and all these fine properties of these stochastic processes and their definition in the continuum, the world of the mathematical physics, is always that there's this sort of a striking feature, which is like when in physics people try to describe interaction at distance between particles or models of interacting particles. Usually the way the description goes is via somehow the fields, right? Sort of the description would be like field description, and which in a way, tells you, okay, you somehow see the effect of the interaction, but you don't really see how it works, right? So, I mean, this is the way it's been going since ever, right? Since Newton, right? You have Newton's law, so you describe the law by how the Earth feels the sun, but it doesn't describe you how the interaction travels from one to the other. And so in the field description, of things, usually you're looking at some object which is defined at every point in space. Say, let's write it like that. And the way things are described is via the interaction at distant points. So it is described usually via something which is related to the correlation function. So correlation function, which will say, you take some points x1, xn, and then you look at something like phi of x1, phi of xn. And of course, phi could be some scalar or something might not commute or whatever. But usually the way the model is described is via, this, the structure and, properties of these type of correlation functions. And of course, there are many good reasons for doing so. The first one is that, then you, instead of looking at describing a space of all possible something in a very high dimensional structure, you are looking at features of functions, and also in terms of experiments, that typically what you're going to, lead to measurable things, because you are going to measure things at given points. And somehow the general ideology was that that's enough, and that somehow the description of these correlation functions is the same as the description of the whole, how the system works. If you know this correlation for any number of points n, then you know how everything about somehow your system, because these phi's are what you can observe anyway. Now, in maybe I could say a little word about how historically things went. So, for instance, in the very early days of constructive field theories, there were ideas that were developed by Simanzik and others, which led to sort of random walk representations of certain fields, and it's in many of the influential work later on. This was sort of in the background. So say Bridges versus Spencer used a random walk representation of spin models and things like that. But somehow these random walk representations were sort of more used as a tool to obtain information about the fields rather than a constructive way to approach them. Now then in the 80s, as everybody knows, there was this the development of conformal field theory that led to a number of developments in many directions. And somehow it just came when only the limitation, of course, one big limitation to try to construct or view something else, construct something else, then understand the correlation functions was well, there are no available tools in some sense to construct anything else. So this somehow this block sort of was removed when Schramm introduced his SLE curves by SLE curves, which were these random two-dimensional geometric curves that you could define by directly globally as using these combination of Brownian motion tools and complex analysis. And so the outcome of these Schramm's construction was random fractal sets that were relevant for the study of these Euclidean some of these Euclidean field theories in 2 dimensions related to conformal field in 2 dimensions. So a cousin of these SLE curves are these things that we call these conformal loop ensembles, which are not just not one curve, but just a whole. Basically, you're given a domain here, and then you have a whole fractal structure that you can sort of define with lots of nested fractal structures, and one of which you could view as at the time candidate for the scaling limit of all the possible interfaces in a 2-dimensional Ising model at criticality, which then turned out to be proof that this is indeed the scaling limit of the critical Ising model interfaces following the work of Smirnov. So these are the conformal loop ensembles that we constructed a bit later. So right, that's around 2010, and then that would be around 2000. And so then basically you realize that there was a tool available using these complex analysis ideas to view some of these fields, interpret some of these fields in terms of properties of random fractal structures. So somehow that you could say if you have a random fractal object, right, say if K is sort of some random fractal with dimension delta in d-dimensional space, right? Then you can look at, what is the probability that x1, xn are in the epsilon neighborhood of K. And this will decay when epsilon goes to 0, like something like d minus delta or something like that, times n. And there will be, if the fractal is well behaved, there will be, this will be the way this will decay at first order, but then there will be something which is a constant term, multiplicative term, that depends on the relative positions of x1, xn, and somehow it tells you, given these endpoints, how more likely or less likely it is that they are all in the same, neighborhood of the same cluster. If K is a, cluster, viewed as a cluster. And then somehow you can sort of view these things here as, cousins of these correlation functions and interpret, these structures there as revealing information about some sort of finite dimensional, marginal distribution of random fractals. So that's sort of the ideology that in some sense the sum of these correlation functions would correspond to reveal structures about random fractals. So one general remark I want to make immediately is that if you are given a set of functions f, so for each n you have a function fn, which is the endpoint function, to know whether this set of functions corresponds to the description of a random fractal in that sense, so that behind the scene there is a fractal such that this will hold for every n and for every point. That's a very difficult thing to check, and it's basically impossible. So somehow the knowledge of all the correlation functions is not mathematically enough to say, well, these correlation functions correspond to the description of an actual random fractal that actually exists. On the other hand, if it does, in some sense, everything about it. Okay, so that's also one reason why getting access to sort of the random geometric structures that might be behind the scenes of some of these correlation function structures is a difficult task if you start from the correlation functions. If you have a constructive way to construct a fractal by other means, then then you can check whether the properties of the fractal would implies the properties that you would expect from these fields, and therefore and if these properties are enough to characterize these correlation functions, you end up with the rules of the games that you have in this sort of on the other side. Right, so that's sort of the general philosophy between what I'm going to say. Of course, in many cases this doesn't work exactly like that. We have to be very careful and so on and so on. But that's just this general framework I want to say. Now, this here, this story here is very much two-dimensional, right? Because it uses conformal invariance in an essential way in order to construct these random families of curves. Now, on the other hand, there's another story that works in any dimensions that sort of emerged when we studied these conformal loop ensemble and defined them together with Scott Sheffield, and that I'm going to start describing now. So in some sense, let me take a new page so that in some sense it's a new start. Now, imagine that you are a probabilist and you're just trying to say, in space, in d-dimensional space, construct the most natural random object you can. And what you want is that the structure you construct in d-dimensional space, has some natural properties, would be, translation invariant, maybe scale invariant. So how do you do that? Well, we have a geometric space, say R3 or RD. And we have one piece of information that we want to use is sort of isotropy, right? Sort of an isotropy. So usually when you have isotropy, you could say, you relate it to the fact that there's a Laplacian, or if you have a Laplacian, then you have a Brownian motion. So Brownian motion is a natural building block to start with when you want to define something random in d-dimensional space. Now, the problem with Brownian motion is you need a starting point. So that's a bit of a problem because you don't want to choose points. You want something like, a bit more, yeah. So, so then the natural thing is to use Brownian loops. Right, so a Brownian loop is just something you can define in any dimension. You fix a starting point, and then you let the Brownian motion run, and you sort of condition it to be back at the starting point at a given time. So this time can be chosen to be, fixed, or it could be chosen to be arbitrary. So of course, the density probability of being back at the origin after time t will be pt of 0, 0 if this is just a transition probability of Brownian motion in d dimensions. So then the trick is to say, well, there's a natural measure. As I said, we don't want to choose points, so we don't want to choose a starting point here. So when you have a Brownian loop, you can define a natural measure on unrooted Brownian loops. So there's a measure on unrooted Brownian loops. So in some sense, you erase the information where the loop is, where the root is, Brownian loops. In many cases, and that will show up later, you can also remove the information about the orientation, whether it goes this way or the other way is, you can remove that information. And there is a natural way to define a measure on unrooted Brownian loops that has the following properties, which is like this measure will be translation invariant, meaning that if you see the loop here, or if you transport the loop, to the right, the measure will be the same in RD, sort of invariant under translation in RD. And it is scale invariant, meaning if you look at the measure mu on Brownian loops and you blow up all the Brownian loops by a scaling factor lambda, then you have the same measure. Okay, so the important thing is, of course, the time length of the loops is not prescribed here. Now, so what you have here, so that means that this measure mu, so this is this measure we constructed with Greg Lawler 20 years ago, which is this Brownian loop measure. So there are a few things you can say. It's sort of the discrete analog, if you want, in ZD, right? Or let's do it in Z squared. To ZD would be exactly the same. Would be just a measure on simple random walk loops that assigns to each loop of length n the measure 4 to the minus n, which is just the probability to do these jumps, these n jumps. Right, so it's a very simple measure, and the feature is that it's scale invariant, so meaning that if I give you any box, right, of size A, right, then the measure, the mass of the set of loops with diameter, say, greater than A over 2 that are in the box minus A to the D, right? This does not depend on A. Right? So this is somehow a very, this measure, and I insist on the fact that, it's just, once you have a notion of isotropy somewhere in any geometrical space where you can make sense of Brownian, then you'll be able to say, make sense of Brownian motion, and you'll be able to make sense of this measure on loops. Now, this is an infinite measure, so this is not really good enough to define one random object, but then there's a very, natural trick, which is just, if you have this measure on loops, well, you just take what we call a Poisson point process. So you fix C positive. So you should view here C as time. And now you're going to do a Poisson point process of loops, of Brownian loops, with intensity. So this is describing the law of this Poisson point process, C times mu. So what does that mean? Mu is sort of some measure, and you can view it as, the information about how likely it is that some cracks appear in space spontaneously. And so, if you wait a certain time, one loop will appear there, another one will appear there, another one will appear there, they all appear, and you wait until time C, and you have this collection of loops that have appeared, in a random way everywhere. Now, the fact that the measure mu is scale invariant, I mean, translation invariance means that the picture you observe is going to be translation invariant in terms of the distribution. The fact that it's scale invariant is going to tell you that actually, everywhere you will have lots of very, 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 very small loops, because at every scale you will have loops that, or that have appeared with a positive probability. And so what you have is locally, you see only finitely many big loops, but infinitely many, many small loops a bit everywhere. Right? So that's this, what we call the Brownian loop soup. That's how we called it. Probably, if you were people, reading Simanzik and all those, you just said it's a good a gas of Brownian loops, right? Maybe we were too two-dimensional and we thought of loop soups, but anyway. So this is this Brownian loop soup is just this gas of non-interacting Brownian loops. And that's a random structure, right? That you can define without, sort of one very natural random structure you want to define in the continuum. You have no tools, you try to define this. Now, the reason, the sort of interesting, historical thing is that this object was never really looked at until somehow we realized that in the two-dimensional case, and then later on, that these collection of Brownian loops were behind the scene in a number of places. So for instance, one I'm not going to describe to you, the Brownian loop soup with intensity when C is equal to 2. For those of you who know Wilson's algorithm to construct uniform spanning trees, if you look at the collection of all the loops you have erased while performing Wilson's algorithm to construct uniform spanning trees, this will be exactly a Brownian loop soup with intensity C equals to 2. So, that's, these objects were sort of at work behind the scenes of a place. And you could say the proof that Wilson's algorithm constructed a uniform spanning tree has to do with the fact that the collection of loops that have been erased is independent of the tree that you are constructing. Okay. But sort of more interesting for us here, there was this remark that in 2 dimensions, okay. And that's sort of this old paper again, I mean, not very new, with Scott, which is like 2010 or something like that, where the story is the following, is that when C is smaller than 1, and you sort of define these clusters of, you look at these clusters of loops, you take the outer boundaries of the clusters of loops that you form. When C is smaller than 1, it turns out that all, these loops do not clusterize into one single cluster. They will still be, separate, different clusters. You take the outer boundaries of these clusters of loops, and you construct exactly these conformal loop ensembles that I told you before. So these will be these conformal loop ensembles that we're describing the scaling limit of the statistical physics models. So CLE kappa. So there's a dictionary kappa as an explicit function of C. And interestingly, what you learn when you do this construction, so it means that out of this simplest tool, which is the collection of Brownian loops, you are going to be able to construct all the possible things that are behind the scenes in these interacting two-dimensional, in these, Euclidean scaling limits of conformal invariant two-dimensional models. And this C is nothing else than what is called the central charge in the physics world, right? So, and there are good reasons for that, but let me not go into that. But that's just to show that using these collection of loops, you are able actually also to reconstruct these, fascinating, fractal objects that are already there behind the scenes in, many aspects of conformal field theory. Now, another remark I want to make now is that in dimension 3, right? Well, conformal invariance doesn't work anymore. Or maybe dimension, let's make just d greater than 3. Conformal invariance disappears. But these loop soups are still there. As possibly interesting tools. To construct physically relevant fractals, random fractals. So now I want to focus on one particular case, which is the case C equals to 1. So by the way, the fact that this doesn't work when C is greater than 1 is because as soon, that's part of this long paper with Scott, that as soon as C is strictly greater than 1, basically all the loops will cluster into one giant cluster of loops in this two-dimensional picture, and there's no geometric curves that you can define anymore when the central charge will be greater than 1, at least in this way. Now the critical case C equal 1, and of course that's not going to be a surprise for anybody in the math physics community, is going to be very closely related with the Gaussian free field. And again, that's not something that is specific to dimension 2. So let me just first note that there's a very special property of this Brownian loop soup. I write it DLS when C equals to 1. And this is what I like to call the rewiring property. So I guess that's 2000, maybe 14 or something like that. And the way you can try to describe it goes as follows. I'm just going to describe it in a very heuristic way. It's just going to say, well, imagine that you see two different loops intersecting here. Or you see one loop making a big, coming back here and then coming back here, making a big loop like this. So here you have a double point. Blue's not good. Yellow here. You have a double point here, and here you have a double point here. So of course, in this continuum world of Brownian motion in dimension 2 and 3, there is it's a problem to quantify. There will be infinitely many double points. You have to measure how many there are. But in some sense, this special rewiring property is already valid in the discrete case where you don't have to worry about this. So let me just try to describe that in that context. Imagine you're colorblind. You're sitting at a double point. You're colorblind, and you see that you have 4 incoming paths corresponding to the 4 half paths here of these two ones or these two ones. And you ask the question, what is, how am I going to, decide who goes with, this one goes like this, or this one goes like that, or this one goes like this, or like that, or maybe this one goes straight and this one goes straight here, right? So you have 3 possible pairings of these 4 incoming half edges, and the rewiring property just says that, conditionally on seeing that, the conditional probability to choose one possible pairing is just 1/3. There are 3 possible pairing independently of everything else. So in some sense, for each double point, you're just choosing at random, how they're going to be paired. And you can do that. You can sort of resample that for all these double points simultaneously in some sense. So that means that, heuristically, if you see the whole cluster of loops, the conditional distribution of how it is actually decomposed into individual loops is chosen uniformly, right? So that there is one object, which is the cluster of loops, and then there is one additional information that you need in order to reconstruct the loop soup, the collection of individual loops, which is just by, doing, you're locally choosing, who go among, the trajectories that come in, who goes out. Of course, if you do that in the continuum, the double points are dense, so you have to, be a bit careful, maybe use some cutoff structure. But that's sort of the idea, is that what you see here is that the cluster of loops itself is very natural object, is a very when c equal 1 is a very, very natural object. Because if you see the cluster of loops, you can reconstruct the conditional distribution of the individual loops by just choosing things independently at random at the different places. And this means that in particular, there are lots of properties of this collection of loops that are reminiscent of, the type of things that Ed Nelson was trying to advocate in the very early days of when you're trying to construct Markov fields, Markov properties of fields with respect to space. And that sort of, structure emerges, naturally for these Brownian loop soup in dimension for C equal 1. All right. So
Wendelin,
the next
is this correct for any dimension, or are you in 2 dimension?
So I'm doing that in 2 and 3 dimensions. In higher dimensions, there's a problem that loops don't intersect at all and don't have double points. So that this doesn't work anymore, but still something very, I mean, at the discrete level, this will still work and will give rise to something important later on.
Okay.
Yeah. So everything I'm saying now is not specific to 2 dimensions anymore. So in particular, it's going to be valid in 3 dimensions, which is probably the one thing I should focus on most now. Now, okay, and then sure enough, it turned out that this, C equal 1 loop soup in dimension 2 and 3, and some version, discrete versions in any dimensions, or versions on cable graphs in any dimension, are actually directly related to the Gaussian free field. So the idea is that the occupation time measure, so this is basically starting with the Lejeune, occupation time measure of the Brownian loop soup with C equal 1. So this is a measure you want to define by saying, lambda puts a mass A, lambda of A. It's a random thing that you, by just define A as a set. For any set in RD, say open set in RD. You just define the total time spent by all loops in A, right? That's what you want to define, where you want to define the total occupation time measure. So then you look at this, you say, well, wait a minute, there's a scaling variance property, and so on, so on. You realize immediately that this is not going to be finite because of the too many small loops. So the total time spent by all the Brownian loops in A, when you look at all the loops of a loop soup in A, this will be infinite. However, what you could do in dimension 2 and 3, you could sort of define the renormalized version of that, lambda tilde of A, which is, the total time spent. Okay, first I do the same with epsilon. I put an epsilon here, maybe choose lambda epsilon here, by all Brownian loops of time length greater than epsilon. How about, then you'll only have finitely many of them, so lambda epsilon of A makes sense. And then you define the renormalized, occupation time, which will be lambda tilde of A, which is just the limit of lambda epsilon of A minus the expected value of lambda epsilon of A. And this one, so the limit when epsilon goes to 0 of that. Right, so you can make sense of a random variable, lambda tilde of A, that tells you, in average, are there more or less loops? That's the total time spent in A by the loop. So is it more than normal or less than normal? And there's another quantity. So the theorem is basically saying that lambda tilde is the same, has the same distribution as a field as the square of a Gaussian free field. And again, the Gaussian free field is well defined. When you look at the square, you have a blow up, you have to renormalize it. And you can do it in different ways. But so basically that would be the square of the GFF. Right. So in some sense, if you see a Brownian loop soup, you can construct out of the Brownian loop soup something which just tells you has exactly the distribution of the square of a Gaussian free field. So there is a direct relation between loop soups and Gaussian free field in this way. Okay, now I probably have to jump. I go to the next. Yeah, I'll be down here. Okay. Now the next thing that next result maybe I want to quote is sort of some results by Aru, Lupu, and Sepulveda, which were all three at ETH Zurich while I was there. So that's sort of a recent stuff, sort of maybe 2018 to 22 or something like that. And it builds a lot on, ideas by Titus Lupu, about how to interpolate between, the discrete world and the continuous world via the cable graph picture. But what they said is that in dimension d equal to 2, there's a direct relation between, you can construct sort of, you start with a Brownian loop soup in a domain D. So in dimension 2, you always need to restrict the domain. You can't do it in R2 because you need the Green's function to be finite, so you need a finite domain. So you start with a Brownian loop soup with C equal 1 in the domain. Each cluster of loops, Ki, of Brownian loops carries very, naturally a measure, finite measure mu I. And then if you define the sum over I of independent coin tosses, so this will be plus minus 1 with probability 1/2 times mu I. Well, this is distributed exactly like a Gaussian free field. So in other words, in 2 dimensions, what happens is that you can go directly from the collection of loops. Each collection of loop, each cluster of loops chooses a sign independently. It carries a special, mu I, which in some sense could be viewed as some sort of a uniform measure on the cluster of loops. And if you just do this, then you just get the Gaussian free field. And therefore, what you see also is that, the correlations of the Gaussian free field will be related with features of these clusters that you have on the right-hand side. For instance, if you look at, something like phi of x, phi of y, which we know is delicate because the Gaussian free field is actually only a generalized function and so on. But if you look phi of x, phi of y, you take the mean value, well, either x and y are in the same cluster, in which case the product will have epsilon I squared, will not be there. And if they're not in the same cluster, then you have epsilon I, epsilon j, independent coin tosses. The mean value would be 0. So this would be directly related with, the probability that x and y are in the same cluster. right? So that these, Green's function, Wick product, decomposition and stuff having to do with the correlation function of the Gaussian free field are related to the fact that the geometry of the clusters here, of these cluster of Brownian loops, have something to do with the Green's function down there. So that means that behind the Gaussian free field, you have these geometric clusters that you can interpret as sort of excursions away from zero of the Gaussian free field. That's the way they do it. And they are just there, and sort of gives a completely different, way to approach the Gaussian free field, where, the fact that it's Gaussian appears a bit like a miracle. But the fact that it's natural and the Markov properties of the Gaussian free field and so on, in some sense, can be viewed as consequences of these type of Markovian properties of the Brownian loop soup that are behind the scene on the other side. So this is the two-dimensional case. So I wrote this paper like some time ago in 2016, where I, wrote down a number of sort of conjectures about what should happen in dimension greater than 3, because there are very interesting features that should go, should work also in higher dimension 4, 5, and so on. About, even though the Brownian loops don't intersect, there is a way to sort of, create clusters of Brownian loops in high dimensions as well. That should be, directly related to the Gaussian free field. So I want to insist on the fact that here, remember here there was this complicated story about in 2 dimensions that the square of the Gaussian free field was appearing as a sort of a first step in order to make the relation between the loop soup and the Gaussian free field. You have to renormalize it, and taking a square of a Gaussian free field doesn't work if you're on dimension 4 and higher. But somehow this thing that you see here is something that is directly valid. Doesn't require the square anymore, and then you sort of see the structure going on here. All right, so what time is it? Okay, so now I should move to the more recent stuff. So new things. So I hope I'll start posting the sequence of papers that are related to what I'm going to say in the coming weeks. So the main thing is it works in 3D. Right. So the idea is that you take a cluster, you take the loop soup in 3 dimensions. In R3. It constructs clusters of loops. And the idea is that, so the first question is, what can you say about these clusters of loops? So the thing is that the dimension of the clusters, as you know, Brownian motion has dimension 2. When you do this multi-scale, because of the scale invariance of the loop soup, you would expect that the dimension of the clusters will be strictly bigger than 2. Of course, can't be bigger than 3. And the relation with the Gaussian free field, and that's sort of what I already guessed in 2016, so that the dimension of the cluster should be equal to 5½ right? So that in 3-dimensional space, you have these fundamental random, clusters that would have this fractal dimension. The fact that the fractal dimension is cannot be larger than 2.5, and sort of was already, in the arguments given there. The main difficulty here is basically how to prove that the dimension is indeed matching this natural upper bound. And so the key there, and again, I insist, the key here and is sort of similar as the key here, which is to use, the GFF and loop soups on cable graphs. So the cable graphs is just this thing where, you have the is Z3 plus, all the physical edges between the points of Z3. And then you take the clusters of loops on cable graphs, and you want to show that the limit of the clusters, where the mesh size of the cable graph goes to 0, is indeed just the clusters of limits, meaning the clusters of macroscopic Brownian loops in the limits. So there's a delicate question here that has to be solved, which is why it took some time. But basically, so it works out, and you can sort of show that the scaling unit of the cluster of the cable graph are a collection of random fractals that each have dimension 5/2. And they can each carry, again, a measure nu. And so these type of sort of some weaker version, but sort of some version of this thing, of the relation with the GFF. The three-dimensional GFF works. So maybe I should mention two open questions. I mean, two open questions already here. Here in the two-dimensional case, using combination of lots of arguments that dig fairly deep into the two-dimensional conformal stuff, it's known that if you're given the Gaussian free field phi, you can recover the clusters of loops that are behind the scenes and the sign here that are behind the scenes. So in some sense, the clusters of loops are functions of the Gaussian free field. An open question in 2D is whether the clusters are actually function of the square of the Gaussian free field, defined in this via the renormalization procedure I described before. And in 3 dimensions, I don't know whether I have no idea whether these clusters of loops here that are behind the scene are actually deterministic function of the Gaussian free field that they're related to or not. Right? So that's sort of one direction I want to emphasize. So now maybe I should give them time, and maybe I should give different flavors to different things. So maybe I want to emphasize one thing first, which is this paper with Lehmkuhler, Mattis, Wei Qian, and so that's 2024. So there we show that in the dimension d equal to 2, something in this continuum world, something nice happens that you don't see, you would not have expected. At least I didn't expect it, which is like if you see the field, if one sees the field phi, as I said, you can identify where the clusters are, but actually not really the cluster. You can identify the closures of the clusters, but there are points, special points, in the closure of some of these clusters that have the probability that sort of this special point X is in some loop. It's part of some loop given phi, right? So you observe the field or the occupation field, and there's a special point there sitting there, and you ask the question, has this point been visited by a Brownian loop or not? And the answer is you don't know, you have to cross a fair point to decide. So in some sense, here there's something subtle going on that tells you that the field doesn't give you all the information about these fractal sets. So in particular, you don't know if one of these points has been visited by a loop, or whether it is actually just in the cluster because there's a chain of loops, smaller and smaller loops, that gets to distance 0 at that point. And you don't know, you have to toss a coin whether to decide whether this happens. So in some sense, you have some uncertainty. If you look at the level of fields, you have some sort of an uncertainty principle about how to decide where the loops have been. So there's something interesting going on there. And it's very important to mention that this happens only because you're in the continuous world. In the cable system or in the discrete world, this would never have happened, but there's something very special going on having to do with the continuum world. Now, a third line of results that I want to mention. So let me do that here. Which is like, of course, when you do these loops, Brownian loops, you want to start looking at interacting loops, because that's what many of you have been doing. If either you're interested in 5-4 models or Bose-Einstein condensation or something like that, then you start having say, yeah, if the loops don't interact, it's not interesting. Let's have to look at the interacting loops. So maybe I want to say a word about 5-4 models. So the first remark is that if phi squared is the occupation time of the Brownian loop soup, when you're looking at the so in some sense you have a discrete random walk. Phi squared would be the number of visits of a point. Now, when you do 5/4, then it's the number of visits squared. And one way to look at the number of visits squared, in some sense, is just say it's the number of double points, right? So the number meaning in terms of time, so the double integral with respect to time of the double points in the loop soup. So a double point in the loop soup means either one Brownian loops makes a double point, or two loops, as before, right, intersect here. And of course, in both cases, it's the same, same as the rewiring property as before. It's a function of the loop soup cluster, the function of phi squared, of course, because it is, whoops, sorry. Yeah. So what you want to do, if you want to define the 5/4 model, which correspond to, GFF reweighted by e to the minus the integral of phi4. So you want to start with a collection of Brownian loops and reweight them, penalize them according to the number of double points that you see in the picture. And so there's a very intriguing fact for me, which is that one person who has been doing things both on the side of the GFF relation with the GFF with Brownian excursions. So when I mentioned Lejean before, some of the ideas there were straight line from what people like to call Dinkin's isomorphism theorem. So Dinkin, he did both, described things having to do with the double points of Brownian motion, saying the motivation was from field theory. And he also had, understood things with the Gaussian free field and how, adding a constant to the Gaussian free field and taking the square was related to something like having to do with Brownian excursion. So he was actually, pretty close to a number of things that I'm going, I have said so far, and I'm going to say now. So Dinkin basically explains how to, in 2D, and then, there were further works by a number of other people, Rosen, Marcus Rosen, Le Gall, and so on. But Dinkin in 2 dimensions started this idea of, there's a way to redefine a renormalized self-intersection local time. So this would be a quantity that could be positive or negative that measures for one given Brownian motion whether it has more or less Brownian loops, double points than it should. So let me just say this. Okay, this is something I have in my drawer, which is that in 2D, one can construct directly these 5-4 models by reweighting a Brownian loop soup by super renormalized, if you want, intersection local time of the loop soup. So in some sense, you take a Brownian loop soup, you define a random variable that tells you how much excess of double points you have in some sense, and then you reweight it by e to the minus this thing, and that's going to sort of construct this field here. And of course, this works because, as we know and is well known, the 5-4 model in 2 dimensions is absolutely continuous with respect to the Gaussian free field. So therefore, you shouldn't be too surprised that it can be represented by a collection of loops, the same as the one that you use to construct the Gaussian free field, but reweighted with the density reweighted. So there's a loop representation of this 5-4 model. Now, more interesting and more difficult, there's this situation of what happens in 3D. Okay, anyway, I'm out of time, so I should say one word what happens about 3D. So in 3 dimensions, as there are a number of approaches of this, how to construct this 5-4 model in three dimensions. And of course, one key word is renormalization. There's also new approaches using dynamical versions of stochastic PDEs, with a paper by Shen and Chibire, for instance, in the last year. But one key word is always to say, well, if you look at this problem, you want to do a cutoff to sort of usually, you have ultraviolet and infrared, bounds, things like that. That means that it's very natural to look at the Gaussian free field in Fourier space and do some cutoff in terms of, Fourier approach. Now, what happens here in the loop soup picture is that a very natural way to do the cutoff, and I've already done that before, is to say, well, let's take a loop soup and keep only the loops of size greater than epsilon. And in some sense, by doing that, you're sort of, destroying the small nodes. So there's a real analogy that says, doing a cutoff by removing all the small loops or doing the Fourier cutoff on the other side, should give rise to similar things. And so what you have in the 5-4 model here, the picture, the way you going to end up representing it is sort of some sort of Markov process that tells you, okay, I know the big loops, and now I'm going to sample the loops at the next size level, and then at the next size level. So you do some sort of renormalization procedure from top to bottom, from big loops to smaller loops. And you look for some stationary measure of, when the Markov chain is just, you penalize these loops according to, intersection local times of these different loops at a different scale. Then you look for stationary measure in that way. And you end up with this idea that you are going to be able to construct the 5-4 field out of a collection of interacting Brownian loops. But the point will be that the collection of all the loops is not absolutely continuous with respect to the collection of all the loops in the Brownian loop soup. However, if I look at just the loops of size, of a given size, you will sort of still see the absolute continuity features there. So it's just it's sort of it's not absolutely continuous model, the 5-4 model in 3 dimensions, but somehow almost. All right, so I hope I managed to give you sort of a glimpse of, this world of what type of stuff one can try to construct using these, elementary building blocks, which are just these Brownian loops, and how they are going to be related with a number of other things that have been done before. So in many cases, one sort of revisits, very well-known stuff. Yeah, okay. So I think that's all I want to say. I can see I'm just been 1 hour now, so I'll stop. Thank you very much.
Okay, thank you very much for this very nice talk. Are there questions or remarks? Please just unmute yourself and ask. Yes, please.
Hi. Do you hear me?
Yes, I hear you. I see that I know you because I see.
Hi.
Yeah, hi. Yeah, hi. Nice to see you. Yeah.
Thank you for the very nice talk. Yeah. So yeah, two questions. One is about Gaussian free field. One can add a mass or even change the two-point function in some arbitrary fashion. Do you have some loose for that?
Yeah.
Arbitrary fashion. And the other one is about in d equals 2, you can add other powers of phi. It still makes sense. You can, like one
Yes.
well-known sine Gordon model, we have cosine. Can you also?
Yes. Okay. So the first thing is mass is not a problem. Everything I did, you could say, you just replace the Brownian motion by a Brownian motion which has a certain, probability to be killed at every time. So in some sense, your Brownian loop of length t will just appear, will be killed with a factor e to the minus lambda t, and so everything works exactly the same. So of course, in two dimensions, I mean, how different the massive field is with the actual Gaussian free field is sort of, but yeah. So mass is not a problem. Let's put it this way. It all works through. And actually, I think this was already, in the setup by Lejean was already had that incarnated. In dimension, so if you want to do these models, so with higher powers, okay, I haven't looked carefully. I mean, of course, in dimension 2, you can do, renormalize self-intersection local time of every power because the Brownian motion will have triple points, fourth point, and so on, multiple points of anything. So you can, in principle, do the power, power law expansion. Now, whether that approach would, lead to something that makes it possible to do things having to do with sine Gordon, I have no idea. I would be a bit doubtful. I mean, on the other hand, there are a number of people who are working very actively on these sine Gordon models these days, so they probably have more to say about that. Having said that, the people who are trying in that direction are usually there's this recent other pillar approach or to the Gaussian free field and to these UV conformal field theory models, which is this constructive way starting sort of from UV theory, starting with the Gaussian free field as a starting block somehow. So this is all the line of thought of Kupiainen and Rod Vargas and so on, Guillermo and others. And they, it's likely that they might have an approach that would lead to things having to do with the sine Gordon field there. So my answer is I have to be, cautious, but yeah.
Thank you. Thank you.
So any other questions?
Hello, my name is Kumagai Takashi. Can you hear me?
Yes.
Yes, hello. I can hear
Hi.
you, and I know
Yes,
you, of
hi.
course. Yeah. Hi, Takashi.
Hi.
Yeah.
I have two naive questions. So one is about the intuitive explanation of 5/2 that is in the screen. And the other question is, okay, you consider Brownian loops, but what about other natural process like stable? Can you think similar thing for the
Okay.
stable loop?
Yeah. So the first thing is you wanted an explanation for this thing here?
Yes, 5/2. This, dimension of that's on the screen. Yeah, dimension of the cluster.
Oh, the highest of dimension of the cluster.
Yeah.
Okay. I mean, the fact that the dimension is 5/2 shouldn't be surprising because somehow what you know is that the correlation function, right? Sort of that appears here would this thing here you will get something which is decaying like 1 over x minus y, right? So somehow the probability that far away points will be connected will decay like a power law like this. And so in some sense, the rule of the game is saying, well, this one has to be connected part of a cluster. This has to be part of a cluster. If they're both part of a big cluster, these clusters are likely to intersect anyway. And then so somehow there should be a 1/2 exponent coming from here and a 1/2 exponent coming from there. And this 1/2 exponent then is this sort of 3 minus 1/2 is 5/2, right? So
Okay, I see.
well, this is just, this is, a very natural thing to expect.
Mm-hmm.
But of course, to make, these type of argument works, you need some quantitative information about how the clusters look like, and that they are, that the randomness of the cluster is sort of evenly spread among the cluster, if you want. Your other question was, stable loops. What are the stables? Well, I mean, I would say, if you try to do something similar with a process which has jumps, you are sort of destroying everything that is at the core of the whole theory, which is that you want this thing to, have a Markov property in space, and you want things to, move continuously. So at the core of all these, all things here and so on, there's the rewiring property and so on. I mean, maybe not for the rewiring property, but at the core of all these things, you always have this idea that you want to you can do. I mean, anything related to Gaussian free field and so on will really, probably be using, if you're in continuous space, the Brownian stuff. Now, if you are looking, on the other hand, things like having to with a lot of the things that Lejean set up is about any Markov chain.
Yes, I
in
remember.
discrete case.
Yes.
So then a lot of things still work. So if you have, as soon as you have exponential waiting times, and so a lot of things would work there. So you could define the loops of any sort, and you would still have the rewiring property. You would still have some Gaussian aspect there, but then somehow you are messing up space by so the fact that the covariance structure is the Green's function, which has this harmonic average property things. This would sort of get into trouble there.
Okay.
So you could do things for other processes, but somehow the Brownian one is sort of clearly has some big advantages.
Yeah, I see. Okay, thank you.
Okay, so there is a question from a chat by Pierre Wang. Hello, I have a question, but maybe I missed a point. What about phi to the 4 theory in 4 dimensions? It is thought to be Gaussian. So perhaps the question is if you can prove triviality of phi to the 4 in 4 dimensions.
Well, I mean, the answer is I don't know. maybe this approach is a way to get there, but I doubt it. I mean, in some sense, 4 dimensions is a delicate thing. So there's, proving the triviality in 4 dimensions was not an easy task. And I doubt that this approach would be much easier. In some sense, both this approach here and this approach there, I mean, for the 5-4 things, I wouldn't say that this is a simpler approach, right, than the existing ones. In many sense, it's sort of more, there are lots of technical things that go into, making it work. But it is, in some sense, enlightening. And also, what I like about this model of interacting loops is that clearly the way you define it, you set it up, makes, you keep this Markov property, this locality feature, that if you know it on the line, you have these portions of loops on one side, portion of loops on the other side. They don't interact with each other as long as they're positive distance from each other. So all these things that, were, elements of the axiomatic approach to these constructing these fields, which are reminiscent of this Markov property of Brownian motion and the continuity of the trajectory of Brownian motion and the definition of the Brownian loop, so are sort of naturally preserved in these ways. Whereas if you have an approach, that builds on doing a cutoff with Fourier, you start destroying the Markov property, and then you have to, work hard to show that you recover it in the end, or things like that. So I think at least it's interesting to know that it exists and there's a way to incarnate these fields.
Okay, so maybe let me ask a question about the simpler model, phi to the 4 in 3 dimensions, which you also mentioned. it is notoriously difficult, I think, to verify all the axioms in whichever setting. For example, to have at the same time reflection positivity and Euclidean invariance. Does your approach maybe help with it?
Maybe. So I mean, the whole idea basically was to, develop an approach that, closing my ears and not looking at what has been done at all, and just trying to, do something at the, at the end, like French people would say, did you reinvent hot water, or, or is it really, interesting? Yeah, I don't know. I mean, the 3D thing, I have to, write it down, and that's sort of a long, it's a delicate thing. As you know, this 5-4, there's the renormalization in all directions because lots of things, blow up, and the fact that the double points are renormalized themselves, creates problem when you want to define the 5, I mean, okay. So there are lots of issues here. But
Okay.
I think it's sort of it is, at least for me, I think it's just that yeah, this approach at least will have very naturally embedded all really physical Markovian type features.
I see.
And yeah.
Oh, but
But now if I take 5/4 in 2 dimensions, then will I get by this approach a complete construction with all axioms, Osterwalder-Schrader, or maybe Nelson axioms? So,
Yeah, I don't know. I mean, again, I haven't looked at the axioms and what you can check them with that. But I mean, my impression was that everything was known anyway, and by all these amazing stuff with bridges and renormalization, that sort of you would yeah, nothing new would come there anyway.
But a reflection positivity is something rather tricky to prove.
Okay, well then.
Oh, but anyway, I have a related question. So
Yeah.
probably a stupid way of asking this question is this your 5-4 theory the same as the 5-4 theory that people are talking about? And of course, this is almost nonsense, but we always have to be very careful what we mean by 5-4 theory.
Yeah. Okay. So I mean, again, now I feel like I'm being pulled in the direction where I'm not competent anymore. What I can say is that this collection, once you do these collection of Brownian loops, you find in 2 dimensions this sort of random variable that measures in some very delicate way some information about how that, how many double points there are that you can interpret heuristically as some way of measuring 5-4. And then saying, yeah, that's the Radonic and the derivatives you want to play with. That this model then has, all the physical, Markov property that I tend to recognize in these axioms is probably true. Whether then it's exactly the same as the one I would expect so, but I haven't checked.
Well, one thing you may try in principle is that this only works for the perturbative region, but if you can construct this and if you can sort of develop renormalized perturbation theory for this thing, and then you may be able to compare it with sort of standard.
Yeah, maybe. Yeah.
Oh, and related question, does this construction work only in weakly coupled regions where the coupling is small, or does it work for strong interaction?
What do you mean? If
It's self-intersection things.
Oh, so what you mean? You mean like a distance?
Oh, no. So you have this thing e to the minus 5/4. Usually you the coupling constant lambda in front of lambda to the 5/4.
So if you want to play with this one.
Is it so you don't assume that this lambda is small or anything like that?
It doesn't seem to be clear yet.
Okay. Very interesting. Thank you.
Anyway, but again, I mean, for as far as I can say, you know, my main interest these days actually is not really on these models. It's really, you know, okay, first, you know, nailing down completely what works in 3D, but then actually what happens in the 4 dimensions and 5 dimensions, because then the story there is, as I sort of outlined, is that the loops don't intersect anymore, but you can still make sense of clusters of loops. There's some sort of a, you know, magic glue in 4 dimensions that agglomerates loops together in terms of into clusters. And that's sort of this, you know, I sort of say a word about this in there. And basically to make all these things rigorous is sort of my plan for the coming months. Yeah. I mean, not all these things, but at least part of them. Yeah.
Okay, any other questions or remarks? If not, let's maybe thank the speaker again and close the official part of the meeting. So I will stop the recording and then there will be still time for informal questions.